Yeah, hello. Thank you to everyone who is still here. Um, I want also to thank Andrea and the organizers for inviting me. Um, so some of you might wonder what I actually am doing here. The reason for that is I think that I was part of the crystal to plate ITN, which was basically the one before the creep one. So I'm basically something like the older brother. I'm still not dead. Okay, and so I have this title for my talk, and I don't know how exactly I ended up in a melt session because it's not necessarily anything to do with melt, but I think it's just a two-phase that made me go to the melt. But okay, so I will talk about deforming two-phase media, and it's actually not melt. So sorry. Okay, so the work I'm going to present is work together with Gregor Golobec and Hauke Marquardt, who are also at BGI in Bayreuth, and also with a bit of that is with Thibaut Duret, who is in Rennes. Okay, so we saw that slide before. This is from Patrick's book about this multi-scale modeling of mental rheology, and I am basically here. So I try to be like somewhere between that and that scale and the lithospheric scale. I try to derive and understand a bit the upscaling properties of heterogeneous media. So in this case, two-phase media. So I just look at two different materials. Why am I doing that? Well, those are just three examples that you see heterogeneities on all scales on the Earth. I mean, you see it basically on outcrop scale. So this is by a paper by Alain and Andrea. You see it in the lower mantle. You have Bridgman, ferropericlase, and you also see it in the lithosphere. That everywhere there are some heterogeneities, and usually what we do in the numerical models is actually we assume just a homogeneous layer. So I also have some models that do that, and we don't really consider what the heterogeneities actually do to the deformation, for example, of our lithosphere, for example, or the crust. And recently there have been more and more papers coming out which actually look at that, and they do have an impact. Specifically because I'm working at BGI, where they have high temperature, high pressure presses, so they do a lot of experiments on lower mantle materials. So this is why my work is also then more tuned in the direction of the lower mantle, but in essence it is a relatively general study on how heterogeneities affect the effective rheology and the deformation of two-phase materials. So rocks are heterogeneous, and particularly in the lower mantle we have Bridgman and ferropericlase which form this mixture, and we would like to know how this behaves, because when you look here in this paper by Vira et al., where they had this Bridgman and ferropericlase mixture and they deformed it in simple shear, they found that basically you have in the ferropericlase or magnesiobustite, that depends a bit on your iron content or magnesium content, you have different stresses in both materials because they have different strength, and overall when you shear the whole thing in simple shear, they start to be, those weak phases become elongated, and the whole rock also weakens. So you see in the end you see a hardening phase and then a softening phase with ongoing elongation. So the question to ask is, okay, how does this elongation then in the end affect our effective rheology? Because in the end we want to basically model the Earth, we want to model the mantle, but we cannot model basically the really small scale on the whole Earth scale, so we want to have some upscaling. And yeah, so we want to capture this elongated inclusion formation. It would be nice if it was sufficiently fast, because otherwise the mantle convection models would take forever. They already take quite a while. And it would also be nice if it's relatively easy to implement, because then the work to be done is just not that much, and you don't have, for example, to change your whole code, but you can just add this little module. So that would be nice. So those are the goals. You have already seen in the last talk the void bound and Royce bound. So those are like the estimates. When you have a two-phase medium, you have like an upper bound, you have a lower bound. We have a mixture of those two materials. When we look here, so this blue one is the void bound, the red one is the Royce bound, and the other one you just ignore for now. The problem with this is that in essence, those estimates are pretty far apart. In that region, so this is for a viscosity contrast of the two materials of 100. So if we just assume the hard material has a viscosity of 1 and the other one is 10 to the minus 2, so this is just non-dimensional, then they are very far apart. So depending on which of the two we would plug in, results will look significantly different. So I'm not the first that actually asked this question. I mean, this has been around for a while, and this is just some papers that looked at that. This whole upscaling thing has been a problem for a long time. I still think it's not exactly where we would like it to be, but a lot of progress has been made in all of those things, and I just build up on that, in essence. So when you look at, oh, I shouldn't breathe too hard. When you look at those experimental thin sections, you see those inclusion and all that. But if you just have one thin section and you model that thin section, you don't exactly know, is this now a representative one, or is it special, or what is the distribution that you can have of those weak inclusions? So for my numerical modeling, I decided to basically artificially generate my own two-phase media, where I can exactly control the statistical properties of those media. So what I do is, I create a random correlated Gaussian field here. So you create basically it's like creating a topography where you prescribe how on average, how far, for example, all the hilltops and like the valleys, how far they are apart. And this is then, basically this is in the Cx and the Cy, which are the correlation lengths in x and in y direction. So you basically prescribe there, okay, how far should they be apart? And so this is the structure. You can also add an angle to that. So basically that some things get then rotated. And you can, with this, you can not only make something that is isotropic, so if those two are equal, but you can also make something that is isotropic. And then I have this, and I can just say, okay, I want 5%, 10%, or 20% of the weak phase, and then I just convert as many pixels above a certain height to that phase, and then I get structures like this. So those are not exactly the same structure that you see in an experiment, but those are the ones I decided to go with first. Okay. And in the end, what I then do is I create this box with my two phases and I just deform it in simple shear. And then what I can do is I can change the Rheology, I can change the volume fraction. Here I will only show stuff where I actually have a linear Rheology, so this n is equal to 1. That's just up to now way easier to handle, and when you want to do statistics you usually need a lot of samples, and as soon as this is larger than 1 you have to iterate, and then things take quite a while. So so far this is n equals 1. And then for example, I can just run one single time step and extract the effective viscosity. How does it look like? So if I shear a medium with those properties here, so the medium looks like this. I shear it in simple shear. This is my stress field, and this is my strain rate field that I get. And down here you see the distribution of the probability density function of the stress in my weak phase and in my strong phase, and here is just the same but for the strain rate. We see the strain rate is strong in the weak phase. And what you see is already okay. The weak phase, you have less stresses because it's weaker, but you also have it is being more deformed, which is quite intuitive in the end. Okay, and then I can basically elongate the whole thing. So what I say is, okay, now set my correlation length in the x direction to a larger value, and what you then get are those elongated inclusions. And you see already that this is completely black. exact some speckles here and here. So that means that actually your stresses drop significantly compared to what you saw before. And when you look at the strain field, you see that all the deformation is basically in those bands here, which correspond to the connecting clusters here and here. So in that case, when it's elongated enough, you just form this percolating cluster, and then the properties of that cluster control anything. This is actually something that depends a bit on how big you make your box. So you have some finite sample effects when you form this. So this is like the numerics just get to a limit because you can make your box bigger and bigger, and then maybe you won't connect from the left to the right side. What you see here then is now that our distributions have changed, especially the one of the weak phase. So you see that you have now kind of this bimodal distribution, and you have this peak here and here, which actually this peak corresponds to this high strain in those bands. And because not all of the inclusions of the weak inclusions take part, just some of them have this high strain. So this is basically what you see as localization. So you can do that for different elongations, and you can look at all those distributions, and in the end you see the stress degrees in the strong phase, and you also see the localization here. So in essence, not surprising, the more you elongate your inclusions, the weaker the material becomes. I mean, this is also like if it's elongated in the shear direction. So this is also not that surprising so far. Oh wait, other direction. Okay, so when I now look at this plot again, so I was at 10% volume fraction of the inclusions, so I'm here, so I'm between those two bounds, and I just plot my the results now of 5,000 samples for each elongation. So this is Cx, this is how elongated my inclusions are, and now I ran basically 5,000 samples for each of those elongations, and then look at the distribution of the viscosity, and I take just the maximum of my distribution as the value for my effective viscosity. This is what you get. So you have this decrease in effective viscosity of the whole sample with more elongation. So in the end, I could, in theory, just take this, fit a curve through it, and then put it in my model. But the problem with this is now for a very specific setup. And that means if I would like to have a parameterization for the mantle, I would have to run loads of those models until I get like a proper description of all the possible cases. So in the end, what I want is some kind of analytical, semi-analytical solution that describes the whole thing better. So what I then thought, well, how do I actually describe my medium? So it's random, so I need to describe it in a statistical way. And so when you look in the literature, there's this thick book that's called, oh, I don't remember. It's about random media, and it's by Torquato, and it's like a very thick thing. And yeah, so when I looked in there, I found there's some function that describe the morphology or topology of those weak inclusions. And one of them, for example, is the one-point probability function, which basically just asks the question, what is the probability of finding a point from the same phase at point I? Okay, so I basically, or of phase 2, for example, of this black phase. So what you do is, you just throw this point I a lot of times in there, and you say, okay, is the black phase there or not? In the end, you just average the whole thing, and then you get a value. In essence, this is just a fancy way of saying volume fraction, because this is exactly what you're going to get at the end. So the one-point probability function is exactly the volume fraction of my weak phase. Now, the two-point probability function, on the other hand, takes 2 points, and it looks at, okay, what is the probability of finding the same phase at point I and point J? Okay, or of finding the weak phase at point I and point J. So you can basically look at that. You can change the distance between those 2 points. You can change the angle to the horizontal, and then you can throw a lot of those sticks around, and you also get basically a certain probability of finding those 2 points being in the same phase. Now you can extend that and ask, what is the probability of finding those 2 points exactly in the same cluster of the weak phase, like here. Okay? And you do exactly the same procedure, you throw those sticks in there, and then you also basically get a distribution. How does it look like? So this is just my example medium here with certain properties. So it's, you see it's elongated here, and it has a volume fraction of 10%. And in the end, my cluster correlation, so the probability that I find at I and j the same cluster, looks like that. Because I can go basically at all angles and all distances, so this is a polar plot. The distance between both points is 0 in the middle and 1 at the outside, and this is just the angle of that. So in the middle of this plot, you basically find the value of your 1-point probability function. So here you should always recover basically your volume fraction, which I do here. So now we see a lot of black here, so that doesn't help much. But when you zoom in, you see, so this is now from 0 to radius 0.1, and then still 360 degrees. You see this elongated shape. And what I plot here is just the contour line where this whole function, so when I fit an exponential function to that, falls off to 1 over e. Okay, and this is actually how the correlation length is defined. And this way, I also recovered the correlation length that I put in originally in my medium. And I also see, well, this looks like an ellipse in the end. So I can basically just fit an ellipse to that and then extract just the 2 axes. And now, the nice thing is that Marcel and Dabrowski et al. In 2012, they published a paper on the effective rheology of a medium that consists of spherical inclusions and the surrounding medium. They deform it in simple shear. They get things like that. But what they actually do is they derive an analytical expression for how the rheology of this medium evolves, how the shear and the normal viscosity. So they look at the strength of everything and the anisotropy of everything. So they basically, they assume it's an ellipsis, or, well, you start with a circle and it becomes an ellipsis, and then you can go from there and derive those equations. So it's actually a coupled system of differential equations where you have the viscosity contrast here, you have the weak phase fraction here, you have an elongation factor, and here you have basically the viscosity. So this is the shear viscosity, and this is the normal viscosity, normalized with the viscosity of the host rock, basically. And I'm just going to look at this for now. Okay, and then what they get is an effective shear viscosity, and then an aspect ratio of their ellipses with ongoing strain, and then they have some expression how that evolves. So the idea was, okay, we use that expression and just apply it to our random medium and see how well it fits. Because our random medium also statistically showed this elliptical shape. So again, you saw that before. You also saw this before, and this is now actually the analytical prediction that they have for the given correlation length. So I think it fits quite okay. I have to admit, not always, so that there's still some things going on, but I think it is very promising to look at this combination of statistical properties and analytical solutions for simpler sets. So then the question is, well, what happens if I deform? Now I have a medium, I deform it, and you see it starts more and more elongated. So this ellipse basically just represents this elongation. Okay, so I want to kind of do that too. So what I could do, I could just, I fit my ellipses, then I basically get my the axes of my ellipses, the length, the aspect ratio of those, because this is really important. And then I get some time-dependent behavior. And so this I showed before, you had this hardening and then the softening. So we also see basically a hardening stage and a softening stage at the beginning. And this is the numerics. This is just from this one sample just the effective viscosity. And now this is the analytical solution, which doesn't quite fit, but it's very parallel. So yes, it needs some tweaking still to if I want to fit it exactly, but I also don't know if this is just a special sample, so I will have to run a lot of samples to get the distribution, the probability distribution for my viscosities here. But in essence, I think this looks very nice, that we can actually to some extent represent our a random medium where you don't exactly know how the weak phase is distributed with some statistical description and then link it directly to the effective viscosity. Okay, so this is basically already the conclusions. Well, yeah, the topology of the weak phase distribution has a strong impact on the effective rheology. Surprise. That was new. So the thing is that the average behavior of this random medium, they can be predicted via this two-point cluster function together with an analytical solution, which still is not perfect, but I think it looks very nice. So so the goal is now to apply this to a lower mantle. I think actually this question of why the spherical inclusion kind of worked for the last talk for this network is also related to that, because it seemed to me that the melt network also looked isotropic. So basically, when you would look at this in terms of statistical properties, you actually get a circular or a spherical kind of distribution function. So this is why I think, yeah. So I thought this actually looks familiar a bit. And of course, not only lower mantle, everything else. I want to model everything else. And just to show an example, so something else that I'm working on is a generation of deep earthquakes through, in this case, shear heating and grain size reduction together. And here you just see a model that is deformed in simple shear. There's some original inclusion in here. I deform it at a certain strain rate, at a certain temperature. And what I plot here is just the horizontal velocity normalized with the background velocity. And the color scale you see goes from -20 to 20, so you can expect some variations there. And what is plotted here is just a timeline. So stress versus the maximum of this, exactly this velocity normalized with the background velocity. So I deform this, and at first you see nothing, but then you come into here, and you see this thing occurring here. You see those peaks in velocity, and you see also this looks strangely familiar, like a double couple to some extent. And you see those peaks, yes, that's what I already said. And wait, there should be something like here, there should be something about the duration of those peaks. So it's about 10 years with maximum velocity of 2 meters per year, which is not an earthquake yet. But the code also can't handle earthquakes yet. So this is still going on. So those peaks recur more often, they get higher, and they get narrow. So I think at the end, with this mechanism, you can actually then generate earthquakes. But now, I reran actually the same model, but not with just a single inclusion, but with a lot of inclusions. So you see them here. So what I plot here is a strain rate at a strain divided by the background strain, so the accumulated strain over the whole sample. And here I plot just the stress. Here is the strain, the background strain, and the average stress in the sample. So I load everything. This is viscoelastic, so I have this elastic loading phase here. And you see already, so those are here all my heterogeneous inclusions, all of those here. When I go a bit further, I'm now at the peak. You see the inclusions even better. But then, at the end, so this was done this week, so it hasn't gotten further in here. What you see is you don't really see the inclusion anymore, you see those bands forming. And those are due to the grain size reduction and the shear heating together. But what I don't see is the same behavior that I saw before, that I see this rupture-like or this really fast localization. And this actually reminded me of the talk we saw before, yesterday, the day before yesterday, about those subduction, the roughness of the subduction, because this is also basically some kind of roughness, and this kind of it seems to prevent in that case, that I get this really fast localization and I get a more distributed behavior. So this can actually then link to other problems too. And that's